In this project, we will use reinforcement learning to perform stock trading tasks. The agent will be the investor and the environment will be the financial market. To form it into Markov decision process, in the state at time t, we will include account cash and the price, holding shares, and technical indicators for each stock. The action for the agent is to buy or sell a certain number of shares for each stock. The reward will be the change in the total account value.
We begin by acquiring our financial data for a selected range of stocks from the Dowser index. We fetch this data using the Y-Finance library, which allows us to retrieve historical market data directly from Yahoo Finance. Data from April 1st, 2009 to January 1st, 2021 are used for training, while data from January 1st, 2021 to June 1st, 2022 are used for evaluating our model performance. After fetching the data, we integrate several technical indicators into our dataset. Specifically, we are using MACD, RSI, CCI, and DX. Each specified technical indicator is calculated using the stock data from API. Also, we calculate market turbulence to measure the instability of the market. We define a look-back period of 252 days, roughly one trading year, to establish a historical context for our calculations. For each day beyond this look-back period, we extract the historical price changes for the preceding 252 days. Then, we calculate the covariance matrix of these historical price changes to understand how stock returns move relative to each other during this period. Next, we subtract the mean historical returns from the returns on the current day to standardize them. Finally, if the covariance matrix is invertible and the dimensions align, we compute the turbulent index using the Mahalanobis distance formula. After all data have been pre-processed, we then train the agents in our environment and get back test results. In this project, we are doing two experiments. First one is training a single model with different hyperparameters, and the second one is building different models and compare the performances.
Experiments, we tested how different hyperparameters affect the performance of PPO algorithm. Our goal was to understand the impacts of varying those parameters, not just find the best result. We selected 6 sets of parameters, each varying in learning rate, bench size, entropy coefficients, and steps per update. By testing those, we observed their influences on trading outcomes. We conducted backtests using historical stock data, analyzing metrics like annual return, Sharpe ratio, and maximum drawdown with Puffalo library. We also compared those results to Dow Jones benchmark. Interestingly, configurations with high learning rates and moderate bench size, particularly configurations like 3 and 6, showed better performance. They adapted well on market changes. In contrast, lower linear rates and smaller bench size don't perform well, and sometimes it results in negative returns.
We also utilize stable baseline theory to train and compare different models, including SAC, A2C, DDPG, TD3, PPO, and recurrent PPO. We use the Dow Jones Index in the same backtesting period as the baseline for comparison. Below two graphs show the result. We can see that TD3 and DDPG generate highest returns. DDPG has 18% cumulative returns and TD3 has 17%. In terms of risk-adjusted measures, such as Sharpe ratio and comma ratio, TD3 and DDPG also have the highest scores. DDPG has the lowest maximum drawdown, which is negative 12%, indicating a lower risk during down markets. These results show that TD3 and DDPG are potentially suitable choices for stock trading, where both return maximization and risk management are critical. In addition, most reinforcement learning models performed better than the baseline, which shows the efficiency of reinforcement learning in solving stock trading tasks.
Here's conclusion. Using only historical data can lead to overfitting, making models that perform well in backtesting but poorly in live trading. Testing in single environment may cause models to overfit specific patterns. It's limited their ability to handle the real-world market changes. While DDPG and TD3 in managing continuous action spaces and risks. So the future work should focus on the diverse training scenario to ensure the real-world applicability.